Here we are given a variable x where the possible values of x are going up by ones. So we are counting, meaning that there is a smallest distance between two different scores. It appears that x is a discrete random variable then. And we're asked if we have a valid probability distribution given here. Now, all of these values add up, all of these values are between 0 and 1 inclusive. So we don't have any negatives and we don't have anything bigger than 1, but we want to make sure that the sum is 1. So I've already opened this up in Excel. Let's take a look and see if the sum is exactly 1. And it is. Let's also see how we could do that on the TI-84. All right, here we go. I want you to see both of them side by side. Take a moment more. All right, here we go. So if I put in the values, kind of predicting what might be coming up in later parts of the question here. 1, 2, 3, 4. Okay, putting in those probabilities. That's in list 2. So now that I've got them in there, if I press stat, calc, one variable statistics, and tell it that it's in list 1 by pressing second and 1, then we are looking. That's interesting. Hold on here. Oh, list 2. Yeah. I said it. That the probabilities were in list 2, but then didn't use that. All right. You can see right here that capital Greek sigma, sum of x equaling 1. That's actually the sum of probabilities. All right, let's see what's next. So we do have a valid probability distribution for a discrete random variable. Because the sum is 1 and everything is between 0 and 1 inclusive. So in different textbooks, you may see a graph looking a little different. You might see something that looks like a histogram instead of this. In other words, you might see rectangles, but it's the same basic idea. So we should see going from 0 to 1 an increase, and then a major decrease, and then these two pretty close together. And it seems to me that it's going to be the first choice, but I'm going to look a little more carefully. 0.325, that makes sense. It's about a quarter of the way between 0.3 and 0.4. 0.393, just being a little bit below 0.4. 0.139, a little more than a third of the way between 0.1 and 0.2. And then 0.72 and 0.71. That one is looking pretty good. Compute and interpret the mean. Okay, so let's see this both on Excel and on the TI-84. Remember that you would multiply the scores times their probabilities. So on Excel, we can do it this way. And then grab, drag the bottom right corner. And then we need the sum. Since I already have a formula for sum here, then I could drag that. I'm getting 1.171. I'm going to check that. And if it's right, then we'll also see it done on the TI-84. All right, let's see it on the TI-84 as well. So going back to our table here, in order to do the multiplication here, go to the top of list 3, tell it to multiply list 1 and list 2. Move this a little bit so that we can both see this. So second and 1 times second and 2. It's going to multiply the things in list 1 and list 2. And then when I do stat calc, one variable statistics, this time for list 3, second and 3, we see it in the second entry. Don't get thrown off by this. That's not taking into account the probabilities. And what the scores were. That's just the mean of raw data there in list 3 to the calculator. But we need to be a little smarter than the calculator. We're talking about the sum. So the sum is 1.171. Okay, what about the interpretation? Even before I read this, the random variable was representing the number of activities a parent of a K to 5th grader is involved in. So I would expect, on average, 1.171. Obviously, no parent's going to be involved in some portion of activities. You know, how can you be involved in 0.171 of an activity? It's probably going to be something about the law of large numbers here. If we do an experiment, no, I do not expect it to be exactly equal to the mean. I don't want to talk about the law of large numbers when the number of experiments decreases. I want to talk about increases. So let's say that whatever size sample they got this from, and then they keep grabbing samples of the same size, keep doing it, keep doing it, keep doing it, and find out what the mean was for each of those. Then take the mean overall for all those different samples. Keep doing this, more and more samples of the same size. I would expect we're getting closer to 1.171 for an average. Compute the standard deviation. Okay, so I'll just do this on Excel because you already saw me set up a formula on the TI-84. It would be similar. What we need to do is take each score minus the mean, we want to make sure that it keeps going back to that row, square that, multiply by the associated probability, add all of these up, and then we would, there is a second version of the formula. I used a different one. Let me see where I went wrong. Oh, okay. Do not divide by the 5. We're not talking about the total number of scores and frequencies here. So backing up, that's all baked into the probabilities. You can think of the probabilities as being similar if this had been empirical probability that's related to relative frequencies. So it's like we've already got that baked in there. The N is already baked in. So I should have taken the sum and taken the square root of that right away. So let's see when we round to one place, i.e. the 10th place, that'd be 1.2, if they agree with that. Scroll. There we go. All right, it's good now. This is a probability that a randomly selected student has a parent involved in 3 activities. That would be exactly 3. So we can just read the table with a 0.072 there. And then 3 or 4. You cannot have both. You would have to go to a different student to get a different answer. So 3 or 4, we're talking about mutually exclusive events. We just add. There's no double counting to worry about. So we don't have to subtract anything out. That should just give us 0.0143 when we add the 0.072 and 0.071. All right, another question shortly.